Hi, welcome to Uptop Solar. My name is Gwendoly, and I am very excited to introduce this new tool, this DC-coupled solar and battery sizing calculator. So this calculator estimates the minimum PV array size and energy output based on your system configuration. So it accounts for inverter limits, charging limits, a DC-coupled topology, and average solar irradiance hours. You use it to explore how different setups affect energy yield and clipping losses. This tool is great for evaluating battery sizing or PV sizing when working with a specific DC coupled system. So if you're wondering something like what battery capacity range makes sense for this DC coupled setup, especially considering power constraints and DC to AC ratio limits, this provides a quick and straightforward first pass check to guide your decision. This can be set up to target a solar array size, and then it will use that target to calculate a range of battery capacity that makes sense with that setup. Or it can be set up to target a battery capacity and then have it suggest a solar array size. What's important to understand is this is made especially for a particular DC coupled topology where the DC to DC conversion is in between the battery and the inverter. You can see the reference image here. So this allows clipping recapture to happen and what this tool is specifically analyzing. Let's go ahead and take a look at the tool. First is set analysis. So this is going to set whether we are analyzing for solar or battery. For example, when we are analyzing for solar, then we will be targeting a battery size. And if we were to click analyzing for battery, then we're going to set a target for solar. So I'm going to leave it at solar. The next is set units, pretty straightforward, kilowatts or watts. It just depends on the size of your system that you're working with. And then the first input is inverter rating. So this tool, in general, there's one exception. This tool assumes that you are exporting 100% of the inverter first out to the load or to the grid, and then anything in excess will be used to charge the batteries. I know in the real world, there are controllers and other settings that you can do to prioritize battery charging. But this tool is a simple check and will not be analyzing that, except for one small exception, which I'll talk about later. So that's the assumption. 100% goes out to the load first, and then everything else goes to the battery. So what's important is to set this accurately. So the inverter rating is 1,000. The DC-DC converter power. So this is saying, okay, well, once the first 1,000 kilowatts goes out to the grid or to the load, how much power can we then put into the battery? So the DC-DC converter, I'm going to set to 1,000 kilowatts for this as well. In fact, I'm going to leave almost everything here in default. The average solar hours, so we're going to put 4 hours. Now, if you want to analyze this, maybe in winter and summer, you can just run this twice. So you can set the solar hours, the lower limit, and then set it to a higher limit, maybe in the summer, and then you could just run the analysis and get a range. But this just does a single solar hour analysis. Next is target battery charge. So this is what we're targeting, the battery capacity that we are targeting. So we have our set analysis to solar, meaning that we are analyzing what's the best solar array for this target battery size. So our battery size is about 1,500 kilowatt hours. One thing to note here, which I have in the info box, there's all these info boxes here, is that I actually add in the logic an extra buffer, considering that there's going to be some efficiency losses from the DC-DC converter and the inverter. So that assumption in the back end is 95% and 98% efficiencies, which actually makes the target a little bit higher, about 7.4% higher than what you actually put in there. So that's something that you might see in the results, that the result capacity is a tiny bit higher than what you have input here because there's efficiencies being considered. Just a FYI. Next is the DC to AC ratio. Now we need to make sure that whatever we analyze, that we're not exceeding the inverter capability of how much PV we can have based on the AC output capacity. And then the recharge days. The recharge days are important because you might not need to recharge your batteries every single day. So the assumption here, when we have it day one, is that all the excess energy after the inverter needs to be enough to recharge that 1500 kilowatt hours. But maybe you could charge it over 3 days, and that means that you could possibly have a bigger battery or a smaller array. So I'm just going to leave it for 1 day. So the assumption here is that we need to recharge based on the excess in a single day. So it's going to target a solar array size based on that. So let's just click calculate and see what happens. Okay, I'm going to jump down to the graph because this makes it a lot easier to see. So you could see the blue part, the first part. So this is all what's being dedicated first to the load or the grid. This is the inverter. So P1 is the inverter power. So we are exporting all the way up to the inverter power, and then anything above that is going to be the green part, which is dedicated to the batteries. And that's what this curve is targeting, is trying to make sure that this green area, which is total energy, is meeting or slightly exceeding your target of 1500 kilowatt hours. And then based on that, and then the yellow is just now actual clipping that we have going on. So what this means is that, the minimum estimated PV array is going to be almost maxing out the DC to AC ratio of about 2,500 kilowatts. The estimated inverter energy available, so this is that blue part that you'd be exporting with that 4 solar hours. So we have 0 to almost 3.9. Will be almost 3,000 kilowatt hours. And then the estimated excess charging capacity, which is this green part, is 1,600 kilowatt hours, which is slightly above what we have requested based on that extra 7% that I talked about. The estimated clip energy then is this yellow, which is 335 kilowatt hours. And then the estimated total unclipped energy available, which is this blue plus green, is about 4,500 kilowatt hours. So based on what our target is, which is this green area, we could have an array that is around 2,500 kilowatts, and that will meet our daily charge. Now I'm going to bump this up to 2. And you can see that since now we have the capability to charge over 2 days, we don't need to charge it every day, that the array actually can be slightly smaller, and we could charge that over 2 days instead of the single day. So you could go ahead and play around with all of the settings here. Now let's change set analysis from solar to battery. Now I'm going to leave everything the same. The default updated my target solar array already, and I'm just going to leave it there too. And everything pretty much remains the same except for the target array. So instead of a battery size, we're going to target a certain array size. I'm just going to leave it in the defaults. I'm just going to go ahead and click calculate since we already went over all of the inputs. And I'm just going to zoom down back to the graph. And it's pretty much the same thing. So the first power is dedicated to the inverter or to the load. And then everything in the green is what we're trying to target or we're analyzing. So at this point, though, the array size is being targeted. So this is being targeted. And then the green part is we're analyzing, saying, okay, what's an appropriate range for this array size? And if we go back up to the results, the range is around 1,600 kilowatt hours to almost 3,000 kilowatt hours. So the way that the upper range in this estimated usable battery range, this 2,981 kilowatt hours is calculated is a little different than what I had explained for everything else. So the 1609 is the green. That's if the inverter were to export everything and the batteries had to be charged up only with the excess, that's that lower range. Now, something a little different is that the upper range actually swaps that. So it's saying, okay, well, what if we were to instead dedicate prioritize the electrons first to the batteries. So pretty much you can imagine this lower half being green. And then after that, we export to the grid. And so you can imagine this middle part being blue. And that's what this upper range is representing. And it's a little bit more obvious if I were to maybe make this 500 kilowatts, for example, and click recalculate. You could see that, the graph isn't representing that. The graph is representing the normal analysis. But you could see that this lower half, the lower range, is now reflecting what this graph is reflecting. So it's saying, okay, then that means the 939 kilowatt hour battery is possible. And then in the background, the algorithm then swaps these two. So it's setting this 500 as the charging, and then calculates what's the total energy that you could have. So if the battery charging were to be prioritized, then you could actually have up to 1,700 kilowatt hours battery. And that's the analysis that happens in the back end. So this is how you get your range. Hopefully that wasn't too confusing, but wanted to explain how this number is calculated, since there's no real indication of how it is. So so that's the results here. So we have the estimated inverter energy available. That's going to be this blue part here, and excess charging capacity is this green part, clipped energy at this point. So because we targeted a solar array, so we're going to stick to it, you're going to have a lot of excess energy. So this might not make sense. Actually, it might make sense if you're trying to maximize a battery size. And then estimated total unclipped energy, meaning the battery plus the inverter, is almost 4,000 kilowatt hours in this configuration. And this is how you use the tool. So if you have any other questions, feel free to put the comments below. Any suggestions, please feel free to put in the comments below. I am cooking up a similar tool that is a little bit more powerful, a little bit more configurable. It probably will take me a while to make, but any suggestions that you might make for this tool could be incorporated in the next tool. So feel free to comment and suggest away. All right, thanks for joining. I hope you enjoy it.